In ancient times, the Greeks recognized some minerals were magnetic, and people around the Mediterranean knew that if they rubbed an amber rod against a cat's fur, lightweight objects would then stick to the rod. As we now know, that behavior is due to static electricity, but back then people didn't know the difference between that and magnetism. In 1600, an English scientist named William Gilbert finally discerned the difference between magnetism and static electricity. But it wasn't until nearly 2 centuries later that French physicist Charles-Augustin Coulomb published 3 papers on electricity and magnetism, where he described electrostatic force. Coulomb's law, also known as the inverse square law, states that like charges repel one another and unlike charges attract, with a force that is inversely proportional to the square of the distance between the charges and proportional to the product of the charges. If that's confusing, here's the equation. This equation says that the force of attraction or repulsion of the charges is equal to K, or Coulomb's constant, times the absolute value of the product of the charges over the distance between them in meters squared. You may now be looking at that equation and wondering how to use it. Or you might not, we don't know. So we'll walk you through a few examples. Let's start with some visuals. Here you see 2 balls, each hanging from a massless string, attached to a hanging wooden rod. This is the digital pith ball lab provided by explorelearning.com. Each ball right now has no charge. Neither is positive or negative. They're perfectly neutral. But if we give them each a charge, one negative and one positive, we can see that they're pulled toward each other. The force between them is attractive. And if we give them 2 negative charges or 2 positive charges, they push apart. The force between them becomes repulsive. Let's say that we have 2 charges, one with a charge of -3 times 10 to the power of -6 coulombs, and the other with a charge of 6 times 10 to the power of -6 coulombs. If they have a distance between them of 4 meters, we can find the electric force between them by plugging these values into the equation we showed you earlier. K is Coulomb's constant, or approximately 8.99 times 10 to the power of 9. So if we plug that in too, and do the math, the electric force between the charges has a magnitude of approximately 1.01 times 10 to the power of -2 newtons. Now this equation is scalar, which means it won't ever give us a negative value, so we have to look at our charges to determine if the force is attractive or repulsive. Since one of our charges was negative and the other was positive, we know that the charges have an attractive force between them, so they pull closer together. If they were both negative or both positive, they would repel or push away one another. Now that you know what it is and how to use the formula, how about some real-world applications? Where is Coulomb's law used nowadays, and what is it used for? Well, a lot of things actually. For a start, the modern copy machine utilizes this concept to work. An element called selenium is a photoconductor, so it's an insulator in the dark, but a conductor in the light. So you know how to copy things the machine shines a bright light on the paper you're copying? Well, the paper is light. The selenium-coated drum's initial positive charge is neutralized, and where it's dark, like where there's writing on ink on the page, the positive charge stays. The copier sprays the drum with toner, a powder with a negative charge, which is attracted to the positive parts of the drum. Then it pulls a piece of paper through, which pulls the toner onto it before going through heated rollers that melt the toner to make it stay to the paper permanently. Other things that use the electrostatic or electromagnetic process include powder coating, laser printers, smoke precipitators, and more. Coulomb's law may have been thought up in the late 1700s, but it has uses and applications that go far beyond what anyone back then might have thought. If you want to learn more about Coulomb's law or any of its applications mentioned in this video, be sure to check the links in the description. Thank you for watching this video, and good luck with all of your future physics adventures.